Imagine having a high-definition TV that is very wide and less than 1/4 of an inch thick, consumes less power than most TVs on the market today, and can be rolled up when you're not using it. What if you could have a heads-up display in your car? How about a display monitor built into your clothing? The possibilities are endless.
Plastic electronics are systems based on electronically conducting polymers, i.e. organic electronic materials, as opposed to solid-state inorganic electronic materials like silicon, gallium arsenide, etc.
An OLED is a solid-state semiconductor device that is about 200 times thinner than a single human hair. A typical OLED is composed of a layer of organic materials situated between two electrodes deposited on a substrate. One of these layers is a light-emitting diode in which the emissive layer is a film of organic compound which emits light in response to an electric current. One way to produce plastic electronics is to inkjet print them. The OLEDs are manufactured in a clean room environment. The manufacturing line consists of sequential processing, starting with substrate cleaning, followed by a plasma treatment, inkjet printing, baking, aligning, cathode deposition, and finally, thin film encapsulation. These processes lead to low-cost manufacturing. They are considered to be far cheaper and faster than the present dominating electronics market of inflexible inorganic devices and printed circuit boards, which use processes like etching and photolithography. First-generation OLED displays have already appeared in large-screen televisions, computer monitors, billboards, mobile phones, personal digital assistants, and cheap, large-area lighting systems. The flexibility of electronic polymers opens up a large range of new applications and markets, such as low-power, self-illuminating wallpaper, paint, and windows, cheap product labeling tags, printed batteries, printed solar cells, and electronic books which can be folded up. But how can we be sure that there are no defects in an OLED display? PlastronicsSpec has the answer. The project's goal is to develop a digital radiographic system to inspect OLED screen panels at high throughput and sentence them as good or bad components accordingly. This technique will allow for fast inspection and application of image processing for the detection of all significant defects, including the OLED pixels, consisting of organic layers, electrodes, and substrate, or other active organic devices, the substrates, and the protective barrier films. What types of defects are encountered?
There are some problems that are occurring during the production and manufacturing of OLED displays, and many of these problems can only be detected after the end of the production. Some of the problems that occur in the OLED display products are chips, cracks, pixel misalignment which affect the color and the image. So these problems necessitate the use of an inline detection system in order to avoid wastage and to avoid defective products getting into the market or getting into an end product. The present techniques for detecting problems are all offline, and therefore cause a lot of delay before the production line can be stopped, and there a lot of product wastage is occurred.
PlastronicsSpec is here to detect these defects. Funded by the European FP7 program, the consortium has developed an automated digital radiography system for high-quality inspection and to ensure the plastic electronic circuits are fit for purpose before leaving the factory door. This approach allows real-time imaging and automatic instant rejection of a defective product and eliminates human misinterpretation that can cause errors in the production system.
This is a system that allows us to inspect organic light-emitting diodes, or OLEDs, also known as plastic electronics. We're able to inspect flat substrates up to an area of 60 by 60 centimeters. We can also do roll-to-roll inspection, which is also another modern method for printing electronics.
PlastronicsSpec equipment has three main parts: the X-ray microfocus source, a flat panel detector with a size of 23 cm by 15, and a mechanical scanner for moving the sample.
Basically, it's a low energy in order to ensure that the components under inspection aren't damaged or destroyed. So this is something that's quite unique for this system. We have a flat panel detector with an active area of 23 by 15 centimeters. We're able to accommodate very large samples because of this XY table here, which moves to the region of interest and allows you to build up a final image of the inspected component.
The analysis part of the PlastronicsSpec software is based on a pattern matching algorithm. The user basically has to define a template, and then the software uses that template to search for defects in the scanned frame. If a defect is found, then it's flagged and its coordinates are written in the database that's automatically created when the sample is scanned.